Good morning, everyone. Oh, excuse me, just a moment. I don't know what's the problem with my... Do you have my screen now?
No. It was up for a moment.
Oh, okay, sorry about it. Just a second. What about now? Do you have it?
Yes, it's there. Do you want to try flipping
okay.
a slide? Make sure it works.
Okay, good morning, everyone. The paper I will be presenting today is soil acidity, lime application, nitrogen fertility, and greenhouse gas emission, optimizing the joint economic management. This is based on the last chapter of my PhD thesis that I did under supervision of David Panel, Tashtamo, Benedict White, and Maxim Polyakov at the University of Western Australia. Soil acidity is a serious threat to crop production all over the globe. And the main reason for this problem is because of crop removal and use of nitrogen acidifying fertilizers, that both of them that they remove cations from the soil profiles. About 50% of world's arable lands and also 50% of Australian agricultural lands are acidic. Western Australia is one of the biggest regions in Australia after New South Wales that suffers from soil acidity. And the main reason of that is sandy soils in this region, which are inherently acidic. That results in about 70% of topsoils and 50% of subsoils to be acidic, and the lost production of this problem would be about $1.6 billion per annum. One of the most common remedy to address soil acidity is lime application, but farmers, they don't apply enough lime to address this problem, to address soil acidity. Because of the cost of lime purchase at the quarry, is transportation, spreading, and incorporation cost of lime application into subsoil horizons. The potential benefits of lime application is about $63 per hectare per annum, or in other words, we can say if we invest $1 in lime application, we can get $11 in return. Lime application can increase greenhouse gas emissions directly and indirectly. When we apply lime into the soil, it reacts with hydrogen ions, and the end product of this process is carbon dioxide emissions. Apart from direct effects, lime application can indirectly increase greenhouse gas emissions through increasing grain production and subsequently higher optimal nitrogen fertilizer rates. To find out optimal lime application rates, there are many complexities. For example, the interaction between lime and nitrogen fertilizers. As you know, different fertilizers, they have different acidification effects. And also the crop rotations, that we know that different crops, they have different acid tolerance degree, and they react to nitrogen or lime differently. For example, legume crops, they fix nitrogen, and that nitrogen would have acidifying effect. The rainfall level and soil acidity levels and also lime application methods would add to these complexities. Having this background in mind, we set our study aim to simultaneously optimize application strategies for lime and nitrogen fertilizer, accounting for the potential interactions and the external cost of greenhouse gas emissions. Also to examine the impact of potential carbon price in the form of carbon taxation of greenhouse gas emissions from both nitrogen and lime applications. And finally, to estimate the net social benefits of such carbon taxation on a representative farm in the study area. We chose the northern wheatbelt as our study area with 3 rainfall zones, low, medium, and high, and with 3 soil acidity severity. When there was only topsoil or subsoil acidity, or both top and subsoil horizons were acidic. To achieve our study aims, we designed a dynamic optimization model consisting of 3 different components: biophysical, economic, and carbon greenhouse gas emission components. The biophysical components looks at the effects of lime and nitrogen application and their interaction on soil pH dynamic, and subsequently on crop yield. And the greenhouse gas emission components predict on-farm and pre-farm emissions from both lime and nitrogen fertilizers. And the outputs from these 2 components were fed into economic components to maximize net present values in order to determine optimal decision rules for both lime and nitrogen fertilizer rates. We adjusted this model for 2 crop rotations, wheat with lupin and wheat with canola, and for 2 nitrogen fertilizer types, urea and ammonium sulfate, where ammonium sulfate has more acidification rate or effect than rather than urea. And the lime application method was set to be surface plus subsurface. This graph shows the on-farm and pre-farm greenhouse gas emissions when there was no carbon taxation incorporated into the system. As you see, the pre-farm emissions were emissions from diesel, lime, and nitrogen fertilizer production and transportation, while the on-farm emissions were from urea hydrolysis, lime dissolution, emissions from diesel on-farm diesel use, from crop residue burning, and indirect and direct nitrous oxide emissions from nitrogen fertilizer and crop residues. In general, based on our result, the on-farm sources contribute as much as 3 times more emissions than pre-farm sources. And the emissions from on-farm and pre-farm sources both vary depending on the nitrogen fertilizer type and the crop rotation. As you see, the total emissions from any sources are about 50% higher when canola was incorporated into the crop rotation rather than lupin. And also, these emissions were higher when urea was used rather than ammonium sulfate. And this is because of additional emissions from urea hydrolysis that we didn't have these for ammonium sulfate source. And the second reason for this would be that ammonium sulfate is more acidification effect than urea fertilizer. This graph, this table shows the optimal lime and nitrogen rates for medium rainfall zone with top and subsoil acidity when the carbon tax was set to be $20 per ton carbon dioxide equivalent. As you see, the incorporation of lupin rather than canola into the system reduces optimal nitrogen rates up to 50%, and consequently the optimal lime and greenhouse gas emissions by 50%. And the use of urea rather than ammonium sulfate increases optimal nitrogen rates, but decreases optimal lime rates because, as I said, it is less acidifying. Both rainfall and level of soil acidity affect the optimal lime and nitrogen rates. The higher the rainfall, the higher optimal lime and nitrogen rates and greenhouse gas emissions. And this was because of the responsiveness of crop production to crop production inputs and nitrogen leaching. This graph shows the absolute reduction in net present value values and emissions when there was a carbon taxation relative to when the carbon tax was zero. The absolute reduction in both NPV and emissions are higher when rainfall is higher, and also canola was used rather than lupin, and urea used rather than ammonium sulfate, as we expected. We did the sensitivity analysis to check how the change of prices would affect the emissions, and we didn't see that much responsiveness of the emissions to the crop to the price changes. For example, for wheat canola rotation, you see the change in carbon price from $0 to $70 per ton CO2 equivalent. The emissions reduced from 23 to 90 tons per ton over 80 years. The change in carbon price changed the net present value and also increased the carbon price, increased the net social benefit of carbon taxation. But the magnitude of those changes were modest. In conclusion, we can say that decisions about soil acidity, lime and nitrogen fertility, and greenhouse gas emissions are interdependent. Optimal rates of nitrogen and lime affected by type of nitrogen and the legume rotations and rainfall. Lime application emits greenhouse gas emissions directly and indirectly via higher crop production, and we can say that incorporation of lupin into crop production or legumes in crop production and use of ammonium sulfate rather than urea would be more socially beneficial. And the carbon taxation could reduce greenhouse gas emissions from lime and nitrogen, but as I said, the magnitude were modest. And we saw very small social benefit of carbon taxation, but the private cost to farmers of such a carbon price is also small. And at the end, I would like to acknowledge my supervisors and scholarships and the financial support I got from Sugar Research Australia. Thanks. Happy to take any questions.